Hello everyone, my name is Ever Barbero and this is video number 3 on materials for MAE 343 and we are in chapter 2. Alright, so review from the last video. We accumulate a lot of knowledge from the last two videos. We have developed conceptual understanding and equations for model elasticity, linear regression on Excel, yield strength, 0.2% parallel line intersects the curve, tensile strength SUT, the maximum on the curve, failure stress, that's a value at the end of the curve. We know what engineering stress and engineering strain are. True stress and true strain, we have two equations for each, depending on what data we have. And we have an understanding of resiliency, the area under the elastic portion of the curve, toughness, the area under the entire curve, and ductility calculated as a percentage reduction of area. Okay, so in this video, we're going to talk about ductile versus brittle behavior, then strength hardening, introduce hardness, talk about cold working and strength hardening, and Bochinger effect. All right, so then from previous videos, we know this is the data that we can collect with a test. That is simple, no big deal. You all have seen the video. And then if we dump this data directly using engineering stress and engineering strain, that are the easy formulas from software mechanics, we get this plot. All right. So, but that plot has some shortcomings when the deformations are large. Due to necking, so we introduce true stress, true strain, and we can draw this plot, which makes more sense for that situation. All right, so that's the background. All right, so then this is just another different figure, similar to this, although this is a real figure from real data, and this is a schematic, okay? So the area under the curve is absorbed energy per unit volume, because this is a stress and this is a strain. So you work out the units, you see that this is energy per unit volume. And you can see here that ductile has high toughness, which is this area, high elongation to failure, this is the elongation to failure right there, and high ductility, which means high reduction of area, which you cannot see here, but we know that the material will neck and this will happen, so reduction of area will be large. All right, these are all desirable properties for structures because when we exceed the design load will be below this point because this is yield. With a safety factor will go down here, but if there is an overload, say you crash your car, you may exceed this value. The structure will suffer permanent deformation because if you go over there when you unload, you go parallel to the original line and you got this much permanent deformation from here to here. That means that you're going to have an indication that something happened. So the fender will be bent. You will see that you have been in an accident, which is a good thing because you fly an airplane and you land and a visual inspection shows that there is something bent, well, better you don't want to fly again, right? So, okay, this is all good things, but it didn't break because to actually break and catastrophically collapse, you will have to go all the way here, and that's a lot of strain and a lot of stress. So it's unlikely that this will happen, okay? Well, if you go to brittle material, everything is the opposite. It has very little area, so the toughness is not there. Elongation to failure, well, is very, very small, and there is no warning. The material goes linear, 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 a little bit of curvature, and boom, it breaks, just like glass. So everybody knows what a brittle material is. So these materials are not that much used, but there are situations in which you have to use them because some of them have properties that are very appealing. Abrasion resistance is one of them. High temperature resistance, ceramics, for example. There might be lightweight, and other unique properties. So when we get to failure criteria, we will talk about failure criteria for brittle material because of that reason. Okay, so we have ductile and brittle. And if you want a quick estimation of how ductile something is or how brittle something is, you go for this value, elongation to failure, because that is reported in the handbooks, and if you can find it, and if the number is large, it's very ductile, and it's very small, then it's not so ductile or even brittle. All right, so this is one way, without having data or anything, that you can tell how good the material is in that regard, ductility. Okay, so now we're going to talk about strain hardening, and main reason I'm going to talk about strain hardening is because this phenomenon it has some use in practice. I mean, there are big industries built around this particular topic. But for me, the most important thing is that this helps me explain fatigue in chapter 6. So really everything I do in the early chapters is to build up the knowledge that is necessary to understand fatigue. So strain hardening means that, okay, by now you know, if I put stress and I go up on this line, which has a slope E, modulo of elasticity E, and I go, eventually I'm going to get to this S sub y, and we know that if we exceed the S sub y, we can keep on going, and I got to put more stress, but the modulus go down, you know, the slope go down, okay, no big deal, and we know that if we get to some point and then we decide to unload, we're going to unload on a line that is parallel to the original. So the modulo of elasticity doesn't change because of plasticity. We go down, and when we get to this point, stop there, and now this is the permanent strain. And since there is permanent strain, that means that the structure is permanently deformed, all right? So this is what happens when you are in an accident with your car. Something gets bent this much in strain. Okay, and if there is a strain, there will be displacement and you will see it. So, okay, fine, so we have this. Then we can load again, but if you load again, you start here. You'll never go back to this point. Yes? Okay, so you unload it here, and now you say, oh, I want to load the structure back up. Now you load on this line, same model of elasticity, and we're going on this line. Everybody understand that? If I went up here, go there, unload, stay there, you don't go anywhere. So now load, you load up, and then you go, reach to this value, which before it was a big deal, but nothing happened, it looks linear, and I can go all the way to this sy prime, because the material is said to have hardened. Yes, really is a misnomer, because the hardness, which is a property, which I'm going to talk about this at the end of this video, it didn't change, but it's said to have hardened in a way to mean that now the yield strength is higher than the original yield strength. So that means that now after you did this one time, then this material is better than this material because it has more S sub y. And in fact, all the tubes that are used for pumping oil and very deep from the ground, fracking and all that jazz, all those pipes have gone this process. Why? Because you pay for a material that is this good, then you stretch it a little bit, and now you have a material that is better. And if it's better, that means that you can go deeper in the hole, in the ground. Deeper because deeper means more weight, more pipe is more weight, and the last piece of pipe that you put at the top of the well, that has to hold the whole length of pipe. So if you want to go very deep, the pipe that is up there, it has to be very strong. So with this, you could go so deep. With this, you could go deeper. So you could go deeper, then you can sell it more expensive, and that's what happened. Okay, so this big industry, yes. Piano wire is the same. You take a wire that is this S sub y, they stretch it, now it becomes stronger. And why you need to make it stronger? Because you have to tighten the wire a lot in the piano. And things like that. Okay, so then you say, oh man, this is free money because I buy this material that has this property, I stretch it a little bit, and I have better material that I can resell for more money. Okay, Good, great. Now, what are the disadvantages that you have for this? Okay, let's see. First disadvantage you have is that now the material works on this dashed line. And if it works on this dashed line, when you go down, you got this permanent deformation. You can never go back there, right? So now your elongation is from here to here. But for the original material, the elongation was from here to here. And the material that has more elongation is more ductile. So you need ductility, let's say crashworthiness. Doing this trick about increasing the SOY may not be so great because you're losing some of this elongation. The plot is for ductile, very ductile metal, but not all metals have this humongous elongation. Sometimes you lose this and you're losing 50%. Anyway, you will lose something. But let's say you go crazy, you want to sell more you want to sell your product and more money. So instead of going hardening from here to here, you say, no, I'm going to harden more. Okay, you harden all the way here. Okay, you harden all the way there. It didn't break yet. When you unload, you go there. Now your elongation is this little bit. So your material is almost brittle, you see? Now what about your toughness? If you harden all the way here, your toughness is this area. So compared to the original has all this area. Humongous toughness, this little toughness. So you lost elongation, you lost toughness, you lost ductility. This is one of the shortcomings, okay? So you have to be aware of that. The other shortcoming that you have is because it's this thing called Bochinger effect. So when you have this material original means annealed. Annealed means I put it in the oven, I cool it down very slow, there is no residual stress, the material is, like I would say, virgin. So, okay, you got the material, you can go to S of Y and you can go to minus S of Y, and it will yield in tension and compression at the same value. Thus, annealed metals work that way. Compression yield is S of Y minus S of Y, okay? And then tensile yield is S of Y, it's the same number. Now, once you start playing these tricks, you go all the way here, and now this distance is the same as this distance, okay? So that means that your compression S of Y is much lower. That means that you cannot take this material that has been hardened and put it in a tension compression job to do it under a state of stress or load that is tension compression, because in tension is great, but in compression is lousy. All right. So Bochinger effect will do that to you. Okay, so that's pretty much it. So, all right, well, this I'm going to mention again because this helps explain how fatigue, how we understand fatigue. Okay. In chapter 6. All right, so then we go here. Okay, so I got to introduce Harnett. Harnett is another simple test. Okay, it's a simple test. Basically, you take either a ball or a diamond-shaped indentor. This is the indentor. And then this is the material that you want to test. And then you push this ball or some other shape. The Rockwell, it has like a diamond, and this is the Brinell is the sphere. And you put the sphere and you push it, and it will leave an indentation there. Then you take the sphere out, and then you look at that indentation with a microscope or something, and you measure the diameter. And okay, guess what? The harder the material is, the less the indentation you get for a given force. All right, so it's a very simple concept. The test is cheap. The test is non-destructive. That means I can go to a bridge and put a portable indentation machine on one of the steel beams, push against it like this, leave this indentation, measure it, and go away. And the Department of Highway never know I did it. Nothing's going to happen to the bridge. No one knows that I put this little indentation there. In fact, there is micro indentation and nano indentation. So you can leave a mark that you cannot even see with your eyes. So that's one advantage. The disadvantage is that it doesn't measure any property directly. It only gives you this hardness. And Rockwell hardness H sub R is not the same as Brinell hardness H sub B. It's just a number. And you can compare one material to the other and say this is harder than the other because, okay, the number is different, all right? The indentation is smaller, so the material is harder. Okay, now, but people have done the hardness together with other tests, say ultimate strength, which is a tensile test. It's not so difficult, but it's destructive. You have to go cut a piece of the bridge, bring it to the lab, and break it, like in the video that I asked you to watch, to find the ultimate strength. And then you have data of ultimate strength and data of hardness for different materials, let's say steel, various types of steels, and you feed that data and you do a correlation. You say, I can approximate, I can guess. This is side where you guess. My SU, T or C, compression or tensile, this is the ultimate strength at the top of the curve. And I can guess that as 1/2 of the Brinell hardness if I'm working on KPSI. Or working the units 3.4 the Brinell hardness if I'm working in MPA. Now, these equations, they don't come from any rationality. I mean, there is no Newton's law or anything like that behind. It's just that I have data of SU and I have data of HB. And okay, I put it on a plot and it looks like 1/2 of HB is SU. These things are called empirical relations, and they're only valid for the material for which they were obtained. So if this is true for some class of material, you gotta be careful not to use it for some other class of materials. All right. So that means that newer materials, this expression may not work for newer materials. And if the steel is, heat treated or an alloy or cold worked, well, this expression may not work. Okay, so you gotta check all these. Then same thing with cast iron. Of course, nobody uses cast iron anymore, but you can check. There are this relationship SU to KPSI and MPA, H sub B. So why do we worry about this? Because sometimes we don't have this property, unlikely because this property is very well known. But in case we don't have it, we can just do this approximation. And for homework, that could be interesting. All right, so this is hardness. When you do the lab 244, I'm sure that you're gonna do one lab for hardness. Okay, so then now we added H sub B, another property, to our list of properties: stiffness, yield strength, ultimate strength, resiliency, toughness, ductility, and hardness. Okay, and with that we have all the properties that we need for now. I say for now because as we move on, there may be some other things that we need. Okay, and okay, we'll deal with that when we need them. And all right, so that's it. Okay, thank you very much.